All right, folks, this is going to be our last video for Unit 3. We'll call this one Bond Polarity. So let's talk about the real story of electron sharing. We want to recall that a covalent bond, by definition, is a bond that occurs between two nonmetals in which electrons are shared. So to give an example, you've got hydrogen, which is always a molecule, so there's two hydrogen atoms that bond together with each other. And when they do that, they share those electrons equally. So you've got a hydrogen atom bonded with another hydrogen atom, like you see right there. And we also have like water. So water is H2O, right? So you've got an oxygen atom and two hydrogen atoms. So we've got a structure that looks like that. We talked about in class why it's bent. It's because of these lone pair electrons giving it that bent shape that leads to a lot of different factors of the chemical reactivity and the physical properties of water. All right, so those are covalent bonds, the sharing of electrons. So each one of those lines represents the sharing of a pair of electrons. Now, the real story comes into the fact that these electrons, this electron sharing, it's not always done equally. Some elements are stronger electron pullers than others, and thus hoard the electron a bit more than their weaker counterparts. So we got to take a look at which electrons are strongest and which ones are weakest. Okay, and to figure that out, we got to understand a term called electronegativity, which is just defined as the ability of an element to pull an electron. That's known as electronegativity, and this is just really essentially based on how much that element itself wants an electron. So if you think about fluorine, which has 7 valence electrons, only needs one more electron to be perfectly stable. It really, really, really wants an electron, so it's going to have a very high electronegativity. On the other hand, sodium has 1 valence electron in its outer shell. It's going to really, really, really want to get rid of that 1 electron, so it's going to have a very low electronegativity. It doesn't want to gain any. The electronegativity number is a unitless number. It's just relative. So what I mean by that is essentially, if you look at this table here, which you can find in your chem manuals, I'll give you a page in a second. If you compare like lithium and fluorine, for example, the electronegativity for fluorine is 4 and lithium is 1, which just means fluorine is 4 times more likely to pull an electron than lithium is. So it's much stronger at electron pulling. So this table, known as the electronegativity table, is on page 121. And if you'll notice a trend on the table, electronegativity increases as you go from left to right. So you'll notice that the lower numbers are on the left side of the table. Okay, these are the lower numbers, whereas the higher numbers are over on the right side of the table. Okay, noble gases are excluded. And it also decreases as you go from the top to bottom. So you'll notice again, some of the higher numbers, or some of the lower numbers now here are on the bottom, and again some of the higher numbers are here on top. And I give you reasons as to why that is over in this box right here. Okay, so if you want to write those down, those are just interesting reasons. Really nothing that I'll test or quiz you on, but people sometimes want to know where numbers come from, and those are some of the reasons why. Okay, so this electronegativity concept, which element wants the electron more than others, leads to different types of covalent bonds. So the first type of covalent bond we'll identify as a non-polar covalent bond. And this is a bond that occurs between elements with the same or very similar electronegativities. So, like, they want the electron equally. There's really no competition between the two. And the rule that we use is that if the electronegativity difference between the two elements is between 0 and 0.4, then we call the bond nonpolar. So with my little cartoon that I have on the bottom here, well, both of the atoms are hydrogen, and if you reference that periodic or that electronegativity table, you'll notice that hydrogen has an electronegativity, I believe, of 2.1. I'm not looking at it right now, but I believe that's what it is, 2.1. So we have two hydrogen atoms, both with an electronegativity of 2.1. So if we subtract that, we get 0. So this is, by definition, this is going to be a nonpolar bond. Okay, and we'll get to what it means to be polar and nonpolar in a little bit. All right, so what's a polar bond then? Okay, well, a polar bond occurs between elements with a larger variation of electronegativity between them. So in this case, one element is just a stronger puller than the other, and my cartoon is showing chlorine as being this like devious element, which is pulling the electrons, and you can notice the electrons are a lot closer to chlorine than they are to hydrogen. Poor hydrogen sweating over there. And so the rule is that the difference in the electronegativities between the two elements is between 0.4 and 2, then the bond itself is going to be polar in this case. Now you might ask, what if the electronegativity difference is larger than 2? Well, in this case, we'd have an ionic bond. We'd actually have a transfer of an electrons. The sharing would get so unfair in this case that the electrons would just pop apart. Okay. So again, what you do is you look up the, if you've got a molecule like HCl, look up the electronegativity for hydrogen, look up the electronegativity for chlorine, subtract those two numbers, and that number that you get, that difference, will be between 0.4 and 2. So in that case, we have a polar compound. We have a polar bond. Right. So polar bonds in their relation to what they actually mean. When electrons transfer in ionic bonds, each ion gains a charge. So we call one ion a positive ion, and we call the other one a negative ion, so a cation or an anion. With polar bonds, electrons don't transfer. They're still being shared. But one element has more ownership of the electron than the other. If I go back for a second to my previous slide, chlorine here certainly has more ownership of the electron than the hydrogen. So this whole idea of this unequal sharing leads to what we call the creation of a dipole. Half of the molecule gets what we call a partial negative charge, and half of the molecule gets a partial positive charge. And I've got that example here. And I actually don't like using hydrogen and oxygen. I want to actually use hydrogen and chlorine. So if you're drawing this little image in your notebook, please put chlorine there on the left, although oxygen would work. So what we notice is we've got hydrogen, which has this little goofy symbol. You draw it like this. It looks like that. That's called partial positive. That's a partial positive charge. And why is it partially positive? Well, it's almost giving up its electron. And so it's almost losing a negative charge, but almost. It's not completely losing it, so that's why we call it a partial charge and use that delta symbol right there. On the other hand, the chlorine, remember we changed that to chlorine, is almost gaining that electron, so we give it a partial negative charge. Okay, partial negative charge. So we say that this particular molecule, which I'm going to write here, CLH, which is kind of backwards, right? We usually write HCl. But CLH has what we call a dipole. And a dipole is just showing you where the electron density is strongest. And so to show that, all we do is just draw a goofy little arrow, and the side that's more positive, we put a plus sign on the tail of the arrow, and the side that has more of the electron, we put a little arrowhead. Okay, so chlorine has more of the electron density, so it gets the arrowhead. So we call this little arrow a dipole. Okay, and you can kind of see dipole. Pole would be like positive, negative, north, south. Di means two, so we have two poles. All right, so how does molecular shape affect a dipole? So the shape of a molecule can allow it to have an overall dipole. And water is a super duper example of this. So if you take a look at water, okay, and you would look at the electronegativity differences between oxygen and hydrogen. There's certainly a difference there. And you would notice that the oxygen atom would have the electron more. Okay, this is a polar bond right there, and this is a polar bond right there. The oxygen atoms would reside more, or the electrons would reside more over by oxygen. Okay, so what that would mean is that we would draw our dipole like this. We'd have an arrow pointing upwards, positive end, and an arrow pointing upwards, positive end. Okay. Now, when you're working with a molecule, sometimes you have what's called an overall dipole, and what you can envision is that, well, most of the electron charge is pointing towards oxygen. So what I view in my head is like, well, just think about me encasing this whole molecule like this. And the top side of that molecule being essentially a negative side, and the bottom side being a positive side. Okay, just like that. All right? So, and that's in effect what happens with the water molecule. Half of it is negatively charged, and half of it is more positively charged. So if I reduce my drawing a little bit, and I draw my water molecule here. And again, I want to understand that this is my negative end and this is my positive end. And then I draw another water molecule here. One thing that you might recognize is that, right here, we actually have a positive and a negative that are next to each other. So what happens is the two water molecules attract. They come together and they attract each other and they kind of cling on to each other. And what's awesome about this is it gives water this really high surface tension. And if you look at the water strider, which is a bug over here on the left side, the water strider uses this property. You can see the water molecules actually form like a pillow. You can see they're actually indented a little bit. That's because the water molecules are clinging on to each other. Okay? And water droplets wouldn't form if it wasn't for this particular property, because all of the water molecules cling on to each other. If you've ever played monkeys in a barrel, which is a little game for kids, you got all the monkeys that hook arms onto each other. That's kind of the idea. That's what water molecules do. Okay, so that's our final video about polarity in Unit 3.